Hi there and welcome to my AP Physics 1 lesson on circular motion. This is going to be maybe a part 2 or 3. Doesn't really matter too much the order at this point, I don't think, but this is an example problem that I'd like to go through that we'll take a look. So here is a mental scenario I'd like to go with you. If you remember Hot Wheel cars when you're a kid, where you run the car through the track and it goes through a loop-de-loop, and you learned that you have to go fast enough that it has to really make contact through the loop the entire time. If you go too slow, it's just gonna kind of go and then fall off the track. If you go too fast, usually that's not too much of an issue with the Hot Wheels, but you'll notice that the track will actually really wobble around. If you can imagine, if you wanted to do that with a real car, the forces acting on the track would be quite severe, and the forces acting on you would also be quite severe. So what we want to do is we want to make it so that way this car, or DeLorean, is going to go up through the track, and then when it gets to the top, it wants to be going just fast enough to where it doesn't, detach off of the track at all, but instead constantly maintains at least some, at minimum, some tiny bit of contact with the track, but not too much, because you're going to be pressed against the track so hard and accelerated towards the middle so hard that you might pass out, that sort of thing. So you don't want there to be too much force. So you want, at minimum, what is your minimum speed to maintain contact with the track as you move along through this track, through its scenario. And perhaps I can express this to you in another way with a ball. So give me a moment, let me grab that. So let me compare this in terms of a string and a ball. This might not be the best because I actually have an elastic string onto this bouncy ball here, but hopefully you'll still get the idea here. So if I were to vertically, okay, and before I had talked about an example where we had a horizontal force acting on this ball, but let's talk about this in terms of a vertical force. So first off, you should recognize that there is acceleration not only towards the center of the circle, but it's also going to accelerate at points in time along its path. When it gets to the top, it's going to start to accelerate, and in fact, when it gets to this position, it's going to be at its greatest acceleration, acting down along the tangent, and then when it gets here, it's going to be decelerating. So we have this force that is occurring, acting towards the center at all times. Let me get a little bit more centered, and so I can go real fast, and there's always a force acting towards the center. When we get to the top, I'm going to go slower and slower. I want to get to a speed just slow enough to where it's, and I can feel it right there. It actually starts to, right, you can even see it. It doesn't make it to the top, and the string starts to go slack. Hold on. All right, so now that we've established why this car needs to always maintain contact, let's go ahead and figure out how fast, and here's my question, how fast would you need to enter the loop? And this is, we're making a realistic, full-size track here. We're going to use an actual DeLorean or some other small car. And we're going to actually figure out how fast someone needs to enter. And imagine if you would actually do this. I figure 40 feet in diameter is about what you would need in order for a car. A car is usually somewhere around 10 to 15 feet long. DeLorean's probably somewhere around 12. And so 40 feet in diameter seems about reasonable, about your minimum diameter. So let's go ahead and determine how fast we do need to enter this loop-the-loop in order to be able to make it all the way around. And you should recognize that as you go up, because of gravity, you're going to slow down, you're going to get to some minimum speed, and then on your way back down, you'll pick that speed back up again, and then leave. And so let's take a look at that. Okay, so let's do some stuff. Let's figure it out. So the first thing to do is to actually look at the top. How fast do you need to be going at the top in order to maintain contact? And so what we will do is we will look at the acceleration necessary. Okay, so at the top, you will be accelerating down. But how fast will you be? At all times, you're always accelerating towards the center of the circle. You're accelerating towards the center of the circle. But at the top, your velocity is at its least. So therefore, your acceleration is at its least. And so how fast are you accelerating? Well, it's v squared over r, because you are accelerating towards the center of a circle, right? Right. You want to make it so that way, okay, let's do this. Let me switch colors and look at something. So what are the forces? I'm going to use blue to represent the forces. So you have a force acting down causing you to accelerate. That force clearly is gravity, right? Let's also look at what other forces. If there is contact between the surface of the wheels and this track, then you also have an additional force. I'm just going to say due to the track. But we want to make it so that way this is at its minimum, so it's effectively zero, right? If you're going any faster, then we do have to add that in. But we want to be moving at a speed, a velocity, where at minimum, the only force acting on you is gravity, which means, let me switch back to red, that means that this acceleration is the acceleration due to gravity, which is 9.8 meters per second squared. So we can just simply set v squared over r equals 9.8 meters per second squared. All right, so let's go ahead and figure out r. So r is 20 feet, but let's go ahead and do some conversion here. Let's convert over to meters. So let's go start off with the 40. Okay, so 40 feet, and to convert, I'll put it over 1. Let's see, there's 3.28 feet in 1 meter, and feet are on top and bottom, and they will cancel. So let's go ahead and do that quick little bit of math. I've got my fancy little calculator guy here. Let's figure this out. So let's see here. We said 40 feet, right? So 40, and we're going to take that and divide it by 3.28 feet. And that should give us about 12.2, seems like a pretty good number. So let's go ahead and I'm going to move my calculator over here. I think that should be totally fine and not too obtrusive. So 12.2 feet is our diameter. Running out of room. So that means that r, and I'll write a little bit bigger here, so that means that our value of r is 6.1 meters. That should have been meters here. Sorry, whoops, meters. And so 6.1 meters is my value of r. My acceleration due to gravity is 9.8 meters per second squared. Maybe I could use 10. It doesn't really matter to me too much. And so what we want to find is what is our velocity at the top. Let me put a t there for velocity at the top. That's what I need to see. So let's rearrange this equation so that way we're solving for velocity. So AR equals v squared, and then I'll take the square root of each side. So v is equal to the square root of AR, or in this case, it's really GR. So let's go ahead and do that bit of calculation. Okay, let's make this a little bit bigger again. And so we said we're going to take the square root of GR. So I'm going to do everything inside of the radical first. So G is 9.8 times R, which is 6.1. And I'm going to take the square root of it, so I'm going to go to the power of 0.5. It's the same thing. And I have 7.73. Okay, so this is, in fact, I'm just going to make that question mark a 7. 7.73 meters per second is your velocity that you would be moving, right, in this direction. That is your velocity along the tangent. That's how fast you'd have to be moving in order to just barely be maintaining contact with the track. So at minimum, that would be what speed you need to go. Okay, so if that's your velocity at the top, then what does your velocity at the bottom need to be? So let me make this this a little bit smaller so we can see the track. So what's going to cause you to slow down? Gravity. How can we go through that mental process? Let's see. You have energy. You have energy down here. It's kinetic. Up here, you have energy. It's potential. And kinetic. Don't forget, you are moving at 7.73 meters per second. So let's go ahead and express that. Let's say that this is position 2, or let's say it's the bottom and top. Okay, so we have kinetic energy at the bottom and no potential energy. so I'm not even going to put it in. That is going to equal the potential energy at the top plus any kinetic energy at the top. Let's go ahead and substitute our equations in for that. So that's 1/2 mv squared. That's the velocity at the bottom. That is going to equal mgy, that is the value of y at the top, plus the 1/2 mv squared at the top. So these are two different velocities. One's the velocity at the bottom, one's the velocity at the top. We know that the velocity at the top is the 7.73 meters per second, and the position of y at the top, let's think about that. From here to here, that's the same as this diameter. That is 40 feet. That is the 12.2 meters. Okay, so let's see, what else can we tell? I would say that if you look, mass cancels just like it does with most of these energy problems. And we just need to solve for velocity at the bottom. Let's go ahead and do that. Okay, so let's multiply each side by 2. That's going to get rid of the 1/2 here, and it's going to multiply this part by 2. Okay. Again, trying to solve for the velocity at the bottom, and now all I need to do is take the square root of each side. So the velocity at the bottom is equal to the square root of 2gy at the top plus the velocity at the top squared. I think that looks good. So let's go ahead and put in some numbers. So the velocity at the bottom is equal to the square root of, I probably could have left a little bit more space there. Let me see if I can fix that. So the velocity at the bottom is equal to the square root of 2 times 9.8. And I'm going to forego putting units in just to save some space. I usually don't do that. So the position of y, that is going to be the 12.2 meters plus the velocity at the top, which is 7.73 meters per second, and we're going to square it. So let's go ahead and put that into our fancy dancy calculator, and let me make that a little bit bigger and even maybe move this guy over. There we go. Alright, so let me clear things out. There we go. Okay, so let's say 2 times 9.8 times 12.2, because that's the diameter, that's the height change, plus 7.73, and we're going to square that. Do not forget to square it. I'm going to hit enter, and then I'm going to take the radical, so to the power of 0.5. 17, and let's round it off to 17.3 meters per second. So the velocity at the bottom is approximately 17.3 meters per second. And that'll be how fast you have to enter the track. Let me move this guy over and go ahead and shrink it down again. There we go. So that's how fast you'd have to enter the track. And you're like, all right, fine, you want to make this real? I don't know how fast 17.3 meters per second is. Let's convert it back. Let's do one final last little step. So we're going to take the velocity at the bottom, which is the 17.3 meters for every 1 second. So we're going to do a conversion here. Let's see, we don't want to go into miles per hour. That's probably what your car reads. All right, so let's move this over a little bit, give myself that much more space. We have meters up top, we want meters on the bottom. Okay, so meters. Let's see, meters and miles. So there's 1,609 meters in one mile. Okay, meters will cancel, and seconds into hours. So let's see, we've got, we want seconds up top, we want hours on the bottom. So in 1 hour, there is 3,600 seconds, and that'll give us our conversion. So let's go ahead and go back to our calculator. I'm not going to bother making that thing bigger. I'm just going to go ahead and go straight for it. So I've got my 17.3, and in my calculator, I'm gonna still go back to my original number, which is 17.2879. I'm gonna use that number, and that's the way you should do it whenever you're doing calculations. You can write down your rounded number, but when you're gonna use that for another calculation, always go back to your original number. So I'm gonna take the 17.28 times 3600, and then divide it by the 1,609. That is way wrong. No, that is right. Yeah, that's right. Sorry. I had a different number in my head for a second. Yep. Okay, good. And we are looking at 38.68. So let's say it's about, okay, it's about 38.7 miles per hour. Okay. So just under 40 miles per hour, if you can imagine that. Okay. So imagine for a moment going just under, just about 40 miles per hour. Maybe you go 1 or 2 miles per hour faster, just to make sure that you don't completely lose traction at the top, because that would be bad. Would you do it? Imagine this track that is 40 feet in diameter. Would you go just shy of that 40 miles per hour? That'd be pretty sketchy. Would somebody ever do it? My numbers are not just random made-up numbers. There's a video, I will link it in the description if this is on YouTube or elsewhere, but there's a video that was done by a British show called Fifth Gear, where they did exactly this using a little tiny Toyota car and made a track that is 40 feet in diameter. Please go watch that, because it's a pretty neat little video to watch. And also pay close attention to their calculations. They glance over it, try and pause on it. Notice that they actually have a number, I think, if I'm not mistaken, I think that their number here is larger, okay, but yet this one is smaller, which means that they did some sort of fudging of the numbers somewhere, which is fine. So our numbers are pretty much dead on. Their numbers are fudged, I think, because they are assuming, for one, that he is going to continue hitting the gas pedal as he goes through the loop, which means that he's adding energy to the system, which is something that we did not add in here. So yeah, I think that's, and plus it's not a completely symmetrical ramp. It might not be exactly 40 feet. With that, I please direct you to watch that video, and I hope you guys appreciate these sorts of examples. You guys have a great one, and I'll see you next time.